right, good morning, everybody. Welcome back to Code 1. What do mathematician mermaids wear? They wear algae bras. Okay, so let's see. I have a quiz from last week, the standard 3 quizzes, which have been sitting on my desk since Thursday. Go ahead and pass those back. Paul. Aiden. Riley. Joseph. Will. Emily. Cecilia. Rachel. Benedict. Kenzie. Avery. Josh. Thank you. Laura. Elise. Ellen. Sarah. Zach. John. Logan. Ryan. Danielle. Sam. And Hannah. Somehow ended up at the bottom of the pile this time.
I had M plus 2 negatives.
Yeah. M plus 2. Yeah, sure. You can go with that. Question, comment?
No, sorry, I'm scratching my elbow.
Ah, I can do that. Okay, so it's been a little while. It's been since last Wednesday since we last had class, so I thought I'd start off by doing a sort of quick overview of what we were looking at in Standard 4. So if you recall, we were on the second page of the Standard 4 packet, and we were looking at the function f of x equals negative x squared plus 8x minus 10. This upside down parabola here. And our goal was to find the instantaneous rate of change of this function at the point x equals 2. And so last time we sort of looked at a few different approximations to what this average rate of change might be. First of all, we found the average rate of change from x equals 2 to x equals 4 using our standard 1 techniques. And we said that turns out that when we draw the secant line of the function between x equals 2 and x equals 4, we got a slope of m equals 2. When we took the secant line from x equals 2 to x equals 3, we got a slope of 3. And then these were both done using the average rate of change formula from a point x0 to x1, which was you take f of x1 minus f of x0 divided by x1 minus x0. In other words, you take the change in the y values between the 2 points divided by the change in x values between the 2 points. And that gave us the slope of the secant line, in this case from x equals 2 to x equals 4, giving us a slope of 2, from x equals 2 to x equals 3, giving us a slope of 3. And what we had done towards the end of class, as a reminder, was we looked at how do we find the average rate of change. And we said, well, if we're looking at the average rate of change from a value of x equals 2 to x equals 4, from x equals 2 to x equals 3, we were trying to approximate instantaneous rate of change, x equals 2, by looking at average rate of change from x equals 2 to x equals several nearby points. And so you all proposed last week that we look at, okay, let's look at average rate of change from x equals 2 to 2.1, from x equals 2 to 2.01. And to basically find average rate of change from x equals 2 to x equals several points that are very, very close to 2, and use that to approximate instantaneous rate of change at 2. And so what we said was, well, instead of just doing that, just doing 2 to different points over and over, let's find our average rate of change from x equals 2 to x equals 2 plus h as some expression in terms of h. And then we could look at what happens if we plug in very, very, very small numbers for h. And look at where if we plug in, say, h equals 0.01, that'll give us average rate of change from 2 to 2.01. And by plugging in very small values of h then, this could give us some approximation for what instantaneous rate of change at x equals 2 itself could be. So first of all, can anybody remind me, why can't we just use this formula and find the average rate of change from x equals 2 to x equals 2? Just use the same point twice?
Because we see dividing by 0.
Yeah. We can't use the same point twice in this formula because we just get f of 2 minus f of 2 over 2 minus 2, which would be 0 over 0, and our lives would be sad. So we can't use the same point twice. But we do want to see what happens if we look at x equals 2 and points that are very, very close to x equals 2. And when we did this, we took f of 2 plus h minus f of 2 divided by the expression 2 plus h minus 2, which last week you all evaluated, came out to negative of 2 plus h quantity squared plus 8 times 2 plus h minus 10. So this right here was our f of 2 plus h expression, where you just take the function f of x, and anywhere that you see an x, you replace your x's with h's. Or, sorry, not h's, 2 plus h's. So this x becomes a 2 plus h, this x becomes a 2 plus h, etc. Minus f of 2, where f of 2 we had already calculated to just be 2. Because if we plug in 2, we'll get negative 4, plus 16 is 12, minus 10 is 2. Divided by the expression 2 plus h minus 2, where the 2's in the denominator cancel out to just give us a factor of h. We then proceeded to simplify this for a bit, and what we ended up with was the expression negative h squared plus 4h all over h. And then let's see, Josh, I think you proposed we could factor out an h from the top and bottom. Leaving us with negative h plus 4 divided by h. If we factor out an h from our numerator, and when we do that, we can then cancel out an h in the top and bottom and say this is just going to come out to negative h plus 4 if h is not equal to 0. Because if h is equal to 0, this expression will be undefined. We just get 0 over 0. But this expression would be, so we need to make very clear that we can't use this expression at h equals 0 itself. And that's where we left off last class. We had this expression for our average rate of change from x equals 2 to x equals 2 plus h. Any questions or comments so far? So using this expression, you can actually make finding average rate of change from x equals 2 to x equals close by points very, very quickly. We could say, for instance, if we wanted to calculate average rate of change from, let's say, x equals 2 to x equals 2.01, we could say, well, 2.01 is going to be equal to 2 plus h, for h equals just 0.01. And so, using this expression, we found this negative h plus 4 expression. What would we get if we plugged in h equals 0.01 into this expression? What? 3.99. So if we looked at average rate of change from x equals 2 to x equals something slightly bigger than 2, it would come out to 3.99. Does anybody want to make a stab as to what they think the instantaneous rate of change of this function would be at the point x equals 2 itself? Josh?
4.
Why 4?
Because that's 3.99, which is close to 4. So if you were to plug in like 1.99, that would be 4.01. So.
Okay, yeah, if we did average rate of change, we could even plug in a point to the left of x equals 2 here. We could say average rate of change from, I'll say x equals 1.99 to x equals 2. In this case, we'll get an h equals negative 0.01. And so our rate of change, using this expression here, would come out to negative 0.01 plus 4, which would be 3.99. Positive that. 4.01. Sorry, Dr. Gerstle understands how negative numbers work. So it certainly looks to be the case that if we take average rate of change from these points x equals 2 to these very close by points, we seem to be getting values of average rate of change that are very close to 4. And x equals 2.01, so if we take rate of change from 2 to slightly to the right of 2, we get an average rate of change very slightly less than 4. If we take average rate of change from 1.99 to 2, so a point very slightly to the left of 2 to x equals 2, we get an average rate of change of something slightly bigger than 4, this 4.01 value. So Josh, you propose that you think the instantaneous rate of change at x equals 2 itself is just going to come out to 4?
Yes.
What would we get if we plugged in h equals 0 to this expression? Someone said something. Why not, Rachel?
It's undefined.
Yeah. We have an issue here in that we can't actually plug in h equals 0 into this expression. Because as we already said, that comes out to does not exist, is undefined. It certainly looks, though, that we could plug h equals 0 into here. We would just get a positive 4 if we did. But that's not going to give us our average rate of change from 2 to 2 in that respect. So here's what we're going to have to do. In order to calculate instantaneous rate of change at x equals 2, we can't plug we can't actually plug in h equals 0 into this expression by itself. But we could certainly do something else using our standard 2 techniques. We could take a limit as h gets closer and closer to 0 and see what that gives us instead. And that's ultimately going to be how we find our instantaneous rate of change, is by taking a limit as h approaches 0. Any questions or comments so far? So I'm going to flip to the next page now. Okay. And here is going to be our kind of formula / definition for how we calculate instantaneous rate of change. It's going to involve taking a limit as h goes to 0 of this average rate of change expression from x equals 2 to x equals 2 plus h. So in general, we're going to define the derivative of a function f of x at a point x equals a to be the instantaneous rate of change at that point. So going forward, whenever you hear me talk about the derivative of a function in this class, what I want you to be thinking is derivative means instantaneous rate of change. And the way we calculate it, we're going to say we're going to define it to be some expression f prime of a, where you see this little, it almost looks like an apostrophe. We read that off as just being f prime. So f prime of a means the derivative of the function f of x at x equals a. And the way we're going to calculate this is to be a limit as h goes to 0 of the average rate of change of f of x from x equals a to x equals a plus h. And that's going to be our instantaneous rate of change formula. Because in order to calculate instantaneous rate of change, we can't take average rate of change from a point to itself. But what we can do instead is to take an average rate of change from x equals that point to x equals that point plus some variable h. And then just take a limit as h approaches 0. Which, when we write this all out, is going to be the same as taking a limit as h goes to 0 of f of a plus h minus f of a all over a plus h minus a, and then the a's in the denominator will cancel out, and what we'll be left with is just going to be a limit as h goes to 0 of f of a plus h minus f of a all divided by h. And that is going to be our derivative formula for how we compute instantaneous rate of change of a function f of x at the point x equals a. So let's see what happens when we use this formula to compute instantaneous rate of change of this function f of x at x equals 2. So in this case, we have our function f of x we have our value of a at a equals 2. That's going to be the x value at which we're computing instantaneous rate of change. So if we plug that in, we'll get that f prime of 2 using this formula is going to be a limit as h approaches 0 of f of 2 plus h minus f of 2 all divided by h. Here, we're replacing a with the x-coordinate of the point where we're computing instantaneous rate of change, in this case 2. And if you look at that, that's going to give us the exact same expression that we had calculated on the right-hand board earlier. It'll give us this whole, I'm not going to go through the computation again, this whole negative limit as h goes to 0 of negative h squared plus 4h all over h, which in turn will give us a limit as h goes to 0 of h times negative h plus 4 all over h. And now, since we're taking a limit as h gets close to, but isn't equal to 0, we can give it the old swoosh swoosh. And say it's just the limit as h goes to 0 of negative h plus 4. And what's going to be our limit as h goes to 0 of negative h plus 4? Here we can just plug in 0 for h, since we're taking a limit, and get negative 0 plus 4 is going to come out to a positive 4. Questions, comments, concerns? So let's take a look at the graph one more time. In general, when we talked about average rate of change, we talked about average rate of change of a function as being the secant line to the function between two different points on the curve. So like this yellow line and this orange line, for instance, that I drew out, we called secant lines to f of x, from 2 to 4 or from 2 to 3. We have a different name for what happens if we take the instantaneous rate of change. That's going to be the value we get from taking the line, and here I'm going to draw this one in white. And now I'll do it, in white. Let's double down. And what we've actually found graphically as value of 4 is going to be the slope of a line that intersects the function f of x at x equals 2, but just kind of bounces off the function there. And does anybody know what we call this type of line? Where we take some type of line that bounces off the function at a single point rather than going between 2 points? Hannah?
Tangent line.
It's going to be the tangent line. So what this f prime of a value graphically is going to represent is going to be the slope of the tangent line to f of x at x equals a. So by computing, this line, the line and the function itself sort of have the same sort of slope going on. They're increasing at the same rate at the point x equals 2 itself. Although if we go to the right of x equals 2 or to the left of x equals 2, this tangent line is going to be changing differently for how the function is changing. But ultimately, finish underlining. Ultimately, what this tangent line is going to tell us in about 8 standards or so from now is a lot of important information about how our function f of x is going to behave. Various different ways. So the moral is, just like how average rate of change correspond to some graphical property of our function, average rate of change gave us the slope of the secant line to the function, f of x, between 2 points. Our instantaneous rate of change is going to give us the slope to what's called the tangent line to the function, where the tangent line to our function f of x is just taken at a single point. The single point where we're computing instantaneous rate of change. Yes?
I guess I'm just a little confused by the whole idea of instantaneous rate of change, because it seems like it just doesn't make sense. Like, how can you have change at an instant? I just am confused by it.
Yeah, it's really, yeah, it's definitely a little bit counterintuitive. What does it mean to calculate instantaneous rate of change at a single point in time? Usually we're used to thinking about rate of change as being distance over time, say, which requires having some positive time interval, or some time interval that's not just length 0 that we're working over. And the way I like to think about it is it comes back to the same idea of, let's say you're driving a car. And let's say that this parabola right here is telling us what's our distance from home. Ignore the parts where it's negative. So let's say if from our distance from home after 2 hours is this, whatever this is, and so at t equals 4 hours, our car stops going forward and kind of starts going backwards towards home. If we think about what instantaneous rate of change is at a single point in time, that's the same as saying, let's say at t equals 2 hours exactly, we're looking at our speedometer. Our speedometer is going to give us a number and say it's t equals 2, oh, you're going at m equals 4. So that would be like saying you're going at 4 miles per hour. Wow, that's a slow, wow, you're really going slowly. It must be learning to drive for the first time. And so, the idea of what is this number instantaneous rate of change telling you is it's not telling you the same thing as average rate of change. Average rate of change is saying, on average, over some time span, how fast are you moving? Instantaneous rate of change is going to be telling us at a single point in time, what's our velocity? How fast are we going? And so you could extrapolate to sort of saying, if we were to keep moving at this point in time, if we were to keep moving at the same velocity for some, let's say for 5 minutes, then the average rate of change over that 5-minute period would give us the same thing as instantaneous velocity at that single point in time. It's definitely hard to wrap your mind around, and it's very counterintuitive. Ultimately, what we're going to be doing, though, in a lot of our later standards in the semester, is using this number, this instantaneous rate of change number, to tell us a lot of important information about how different types of mathematical objects, different types of mathematical expressions are changing over time. So later on, we'll be answering questions like, let's say we're pouring water into a container, and f of t tells us at time t, how much water is in the container. Instantaneous rate of change at, say, t equals 3 minutes will tell us at that point in time, how fast is water entering the chamber. It's going to give us some notion of, at a single point in time, how fast is something changing. If we were to sort of take a photo and assume that the function was changing at a constant rate, along some interval of time, at a single point, what would that constant rate look like? Sorry, that was kind of a long-winded answer to your question, but trying to give some physical examples of what we're going to be looking at. And I think over time, the more we deal with this expression, the more sense it'll start to kind of make intuitively as to what's going on. There's also a bunch of other sort of graphical ways of interpreting it that we're going to be getting into the next couple of standards. Any other questions or comments so far? Let's look at another example where we're going to look at another function and try and compute instantaneous rate of change at a single point. So the next function I want to look at is going to be the function g of x equals 3 minus x squared. And I want to compute instantaneous rate of change of this function at x equals 4. At a single point in time, x equals 4. So if we graph this out, we're going to have a parabola again that's upside down. And the point at which we're going to be looking at x equals 4 is going to be somewhere about here. And our goal is going to be, let's use this formula to compute instantaneous rate of change. Question. When we compute instantaneous rate of change of this function at x equals 4, are we expecting to get a positive number or a negative number for instantaneous rate of change, instantaneous velocity, say, of this function? Mark?
Negative,
Why negative?
because the tangent line is like this.
Because the tangent line moves downwards as we go from left to right?
Yes.
Yeah. If we were to sketch out a graph of our tangent line here, certainly looks like this tangent line here is going to end up having a slope that is negative. Meaning as we move from left to right on the graph of our function is moving downwards. It's decreasing, so to speak. So let's see what happens when we compute this and see if we come out to a negative number at the end. So here, to say that I'm going to take instantaneous rate of change, I'm going to write g prime of 4. Prime means instantaneous rate of change. It means we're taking a derivative. So by the definition, g prime of 4 is going to be a limit as h goes to 0 of, let's see, we're replacing f with g since g is the new name of our function. G of a plus h, so g of, in this case, 4 plus h, minus g of 4, all divided by h. How are we going to compute g of 4 plus h? If we're replacing our x's with 4 plus h's, what is that going to give us here? This is kind of the trickiest part of the process, in my opinion. Josh?
Because the equation's like g of a plus h, where that 4 is, we'd plug in 3 minus 4 squared.
Okay, so that would give us 3 minus 16 is negative 13.
Yeah.
So this expression would come out to minus a negative 13. And how about g of 4 plus h?
You have to square the binomial.
Ooh, so how would I write that out without squaring anything first?
So you do
3 minus the quantity 4 plus h squared.
Like that? Yeah, nice job. That's exactly it. So when we take g of something like 4 plus h, it may seem daunting to try and say, what does that mean? Like, how do we write that out? But the general idea is always, you go back to your original formula for g of x. And what you do is anywhere that you see an x, you replace it with whatever you're plugging into the function g. So if we're going to take g of 4, we replace our x with 4 to get 3 minus 4 squared, which is 3 minus 16, or negative 13. If we're taking g of 4 plus h, then anywhere we see an x, we're going to replace it in parentheses with the expression 4 plus h. And so that'll give us 3 minus the quantity 4 plus h squared. So that's why we have to plug in this 4 plus h into this quadratic here, and we'll end up having to square it in the next step, is because our function says, in order to plug in thing, we take 3 minus thing squared. In this case, our thing happens to be 4 plus h. So 3 minus thing squared, in this case, will come out to 3 minus the quantity 4 plus h squared. Minus g of 4, our thing is 4, so 3 minus thing squared becomes 3 minus 4 squared, which was negative 13. All over which, of course. Okay, so we're going to have 3, and we're going to have to, unfortunately, square the 4 plus h term. How do we square 4 plus h? In other words, if we were to multiply out this expression right here, what would we end up with? Cecile?
Negative 16, or 16 minus 16 plus 8h plus h squared.
Looks like and then when we apply the minus sign, all of these terms end up becoming negative in the next step. Yeah, if we square this, we'll get a 16 plus 4h plus 4h, so plus 8h here, and then plus an h squared term. And then we'll divide everything by h. So since you seem to have already done it, Cecilia, what happens when we distribute this minus sign?
Basically, all those, like the 16, the 8h, and the h squared all become negative. So you end up with a negative 13 minus 8h minus h squared plus 13.
Okay, so we end up with something like this, in other words. Yeah. So something to keep in mind is when we're subtracting off this expression in parentheses, a very easy mistake to make is to forget to distribute the minus sign. So since we're subtracting off this whole thing, keep in mind that this minus sign is going to have to distribute to every single term in the sum. So it becomes minus 16 minus 8h minus h squared. It's easy to forget to distribute the minus sign, which is why I'm making a big deal about this. Yeah, nice job, Sid. Ooh, this looks nice. 3 minus 16 is negative 13. And we end up with a positive 13. So I think some swooshing is in order. And if we were to take a limit of this expression as h approaches 0, What are we going to find?
Zero, zero.
0 over 0? Gadzooks. That's sad. So we can't just plug in h equals 0 into this expression.
If you cancel out your h's, or factor out an h, then cancel them.
Ooh, okay. You want to cancel out the h in the denominator with the factor of h in the numerator? That sounds good to me. Let's try that. So if we factor out an h in our numerator, what are we going to be left with, Jeff?
Left with a negative 8 minus h.
Okay, and then that'll all be dividing by h. Swoosh, swoosh. And we end up with just a limit as h goes to 0 of negative 8 minus h. And how do we compute that?
You just put 0 in for h and the answer is -8.
Negative 8 minus 0 equals negative 8. Everyone all right with that? I like it. Neato mosquito. So it turns out that our instantaneous rate of change to this function, g of x, at the point x equals 4, is going to come out to a number of negative 8. Great. Which I like. You all said, let's see, Laura, I think you said that this is going to come out, that you thought this was going to come out to a negative number. Negative 8 seems to be a negative number to me. So that's a good sign. It's a sign that the answer we got kind of meshes up with what the type of answer we expected to get, which was a negative answer. So we now know exactly what this slope is. We can say something better than m is negative. We can say it comes out to negative 8. Yes?
Do they always come out like nice and neat at the end like this with like 2 or 3 numbers where we can just plug in 0 for h and
Oh, I think you know the answer to that. This one you might think was kind of nasty and long. I assure you it can get nastier and longer. Does it come out to something where we can just plug in h equals 0? In general, the answer is going to be yes. There are times when the answer is no, and for that we will see in standard 14, 13? Standard 14, I think, which is all about what happens when taking the derivative goes terribly wrong. We'll look at some examples of that. And basically that'll be functions like, I'll give you a slight spoiler, like the absolute value function, where if you tried to take a tangent line at x equals 0, it gets into trouble with like, how do we draw a tangent line to this thing? There's infinitely many lines that we could draw. And those will be types of functions where if we went through this process, we would find that the limit comes out to something not so nice. I could also give you something in theory. I'm not going to. Let's say instead of 3 minus x squared, it was 3 minus x to the 12th. Where you would have to calculate 4 plus h raised to the 12th power. 3 plus h, 4 plus h times 4 plus h times 4 plus h 12 times. Can you do it?
Theoretically, yes.
Theoretically, yes, Hannah? Practically speaking, that sounds painful and miserable and you don't wanna? I agree. That would be my answer to that too. If you ask me, Dr. Gerstle, what happens if we multiply that out to the 12th power? I can hear some of you stewing in the back of the room. You're thinking to yourselves, Dr. Gerstle, let's go back to the original equation. Can't you just take the derivative, get negative 2x, plug in x equals 4 to negative 2x, and get negative 2 times 4 is negative 8? In other words, the easy way. And the answer to that is going to be, you can do that once you get to standard 5. Slight spoiler alert for standard 5. There is an easier way to do this. That doesn't involve taking a limit. It doesn't involve plugging this in. And from standard 5 onward, you can use the easier methods. But I want to see you do it the harder way a couple times. Get 2 masteries in standard 4. And in standard 4, we're not going to use the, quote, easy method, unquote. The reason is because I think it's important for you to kind of see conceptually where is the derivative coming from. It's coming from taking this limit as h goes to 0 involving the average rate of change function. And I really want to drive home this point, that by taking a limit as h goes to 0 of this expression involving average rate of change, that's how you compute instantaneous rate of change. Because once we get to all the shortcut formulas, those might be easy to use, but there's not really going to be much intuition as to where did these shortcut formulas come from. But this, it's a harder formula to use, but we can sort of see the different steps as to how did we get this formula. It came from computing average rate of change from 4 to 4 plus h, and then taking a limit as h goes to 0. In other words, taking average rate of change from 4 to really close by points, and then letting the distance between those close by points shrink closer and closer to 0. So we end up taking average rate of change of points from x equals 4 to points that are getting closer and closer to 4. Any other questions or comments? You're all asking some really good questions. So. Okay, let's do another one. There's an example, by the way, involving x cubed at the bottom of the page. I'm going to leave that one as an exercise to you. Let's look at a more spicy function. Instead of these parabolas, let's take a look at a square root function. So this time, our function, k of t, is going to be equal to square root of t plus 1 at the point t equals 4. And let's try to make it a little better. So I'm going to compute instantaneous rate of change of this function at the point 4. Dr. Gerstle, there's t's and not x's. Oh my good golly gosh. Practically speaking, that's not really going to change anything. Anytime we see an x in our formula, we're just going to replace x with t instead. It's not really going to affect anything. So what type of answer are we going to expect to get? Positive number or a negative number? A big positive or a small positive?
Small.
Why small positive?
Because if you draw the tangent line to that point, it's going to be like small slope.
It's going to be a line with a really small slope? Yeah, I would say so. That if we look at this tangent line, it has a positive slope because as we go from left to right, our line is moving upwards, but also it's barely moving upwards. It's moving upwards very, very slowly. And so we would probably expect that our tangent line is going to come out to some small positive number, maybe like a half or a third. So now, if we want to compute k prime of 4, or we take the derivative of our function at x equals 4, get this chalk. We're going to have to use the limit as h goes to 0 of k of 4 plus h minus k of 4, all divided by h. Do the same process we've done before. So can anybody tell me what k of 4 plus h is going to be in this circumstance? Rachel, you want to give it a go?
Is it the square root of 4 plus h plus 1?
Like that? Everybody okay with that? I like it. Now, we take our expression k of t. Anywhere we see a t, we're replacing that t with a 4 plus h. And so square root of thing plus 1, if our thing is 4 plus h, becomes square root of 4 plus h plus 1. Which we could simplify to square root of 5 plus h if we wanted to. How about k of 4? We plugged in 4 into our function k of t. What is the function going to output?
Square root of 5.
Square root of 5? Let's see. 4 plus 1 is 5. Square root of 5 is square root of 5. And so what we'll end up with, I'm going to go ahead and simplify inside of the square root here. Save us a step. We'll end up with square root of 5 plus h minus square root of 5 all divided by h. Neato burrito. Can we factor out an h here from our numerator? Well, let's first of all, let me back up. Can we plug in h equals 0? That?
No,
Why not?
you get 0 over 0.
The classic problem of you always get 0 over 0 if you try and do that. We can't plug in h equals 0. Is this something where we could easily factor an h out of our numerator to cancel out with the denominator?
No, because the negative square root of 5 doesn't have an h in it, so it could be dividing that by h, because it would be an h to factor out.
Yeah, we can't really pull out an easy factor of h here because from our numerator, there's not a nice factor to pull out like there was in this example. Could we try doing this? Square root of negative 5 plus h. Could we rewrite that as square root of negative 5, or not negative 5, square root of positive 5 plus square root of h? We could, that'd be nice, because then we could just cancel out the two square root of 5 terms and end up with square root of h over h, which is not so bad. If only we could do that. Unfortunately, square roots don't have that property. You can't take the square root of a sum and write it as the sum of the square roots. You can do that with products. If we wanted to, we could take something like square root of 5 times square root of 5h and write that as square root of 5 times the square root of h. That's something that'll work out nicely for us. But we can't do that with sums. It's a very common mistake, and one that I've made myself a number of times, which is why I'm trying to write lots of scary warnings on the board about this. But the problem is, you can't actually do this. You can't take the square root of a sum and write it as the sum of square roots. So, it's kind of a nasty expression here. This is not something where we can easily factor out an h or plug in h to the top and bottom. So I think what we'll have to do is going to involve some trickery. Check this out. Is everyone okay if I take the limit and if I take this expression and multiply it by 1? That shouldn't change anything, right? We multiply by 1, nothing changes. So I'm going to multiply by 1. But I'm going to multiply by 1 in a sneaky way. Because the 1 I'm going to multiply it by is going to be square root of 5 plus h plus square root of 5 divided by square root of 5 plus h plus square root of 5. After all, that just should come out to 1, right? Because everything in the numerator cancels out with the denominator, since the numerator and denominator are the same, so it just comes out to multiplying by 1. Dr. Gerstle, why would you do such a thing to us? Bear with me for a second. What I'm going to do when we multiply fractions, by the way, if I have two fractions, a over b multiplied by c over d, how do we multiply these fractions together? Uh-oh, Dr. Gerstle is asking us about old school math.
Cross multiply.
Cross multiply? Ooh, so take AD over BC? I think that's something you would do if you wanted to get like a greatest common factor of these two fractions. But I don't think that's necessarily what we do when we just multiply the two fractions together. There you go.
Wouldn't it just be like AC over B?
To just multiply the numerators and then multiply the denominators? I think so. When we take two fractions like this and multiply them, we could just multiply the numerators and then multiply the denominators straight across. We can't do that if we were adding the fractions, but multiplying fractions is actually pretty nice. You just multiply the numerators and you multiply your denominators. So let's see what happens when we do this. In the numerator, we're going to get square root of 5 plus h minus square root of 5 times square root of 5 plus h plus square root of 5 divided by h times the quantity square root of 5 plus h plus square root of 5. Holy guacamole. This is going to be fun. Let's FOIL this out. What happens when we take square root of 5 plus h and we multiply by square root of 5 plus h? We multiply our first two terms. All right.
You get 5 plus h.
Oh my gosh, square root of thing times itself is just going to give you the thing inside the square root. So square root of 5 plus h times square root of 5 plus h is going to give us a 5 plus h term. Minus square root of 5 times 5 plus h, we combine these two terms, plus square root of 5 times 5 plus h if we multiply the outer terms, and then finally, minus square root of 5 times positive square root of 5, it's going to give us a minus 5. All over h times square root of 5 plus h plus square root of 5. Is there anything we can do to make this expression look nicer? It's getting scary.
get square root of 5 times 5 plus h, because there's a negative and a positive.
Ooh! Give the old swoosh swoosh. Cancel out. Yeah, so that's nice. So we end up with 5 plus h minus 5.
It's just h.
Yeah.
The 5's cancel out, so it's just h.
Oh, hey, more canceling. This just comes out to a limit as h goes to 0 of just h divided by h times square root of 5 plus h plus square root of 5. Okay, so the numerator actually canceled out pretty nicely. Yeah.
Now you can cancel out the h's.
Oh, hey, now we have some nice factors of h in the numerator and denominator that'll cancel out. So we'll have a factor of 1 left in our numerator. Because if we cancel out a factor of h from h itself, we'll end up with 1 every time, because h divided by h is 1. All right, and how can we then, so then we take a limit as h goes to 0 of 1 over square root of 5 plus h plus square root of 5. What do we do at this point with this expression?
Technically, everything in the denominator is to the negative 1/2 power.
True.
So you could bring it up.
Ah.
Negative 1/2.
Write this as 5 plus h plus 5 to the negative 1/2.
Or separately, yeah, but.
I think you're trying to do something like this.
Not like that, but like, bring each one up.
Oh, I see.
Separately.
You could rewrite the denominator as something like 5 plus h to the 1/2 power plus 5 to the 1/2 power. But we can't bring those terms up to the numerator separately and say multiply by these things to the negative 1/2 power, because that would be technically breaking a more general version of that second property. Yeah. Exponents and sums don't behave nicely, unfortunately. So it's good idea, but I don't think that's going to really help us here.
Can't we just plug in 0 for h now?
Oh, hey, we're no longer going to get 0 over 0 if we plug in 0 for h. In fact, we get 1 over 2 root 5. And that is our final answer. Because square root of 5 plus 0 is just square root of 5, and square root of 5 plus square root of 5 becomes 2 root 5. So what's the moral of the story? Moral of the story is if you have square root of thing minus square root of thing in your limit here, try multiplying top and bottom by square root of thing plus square root of thing instead. Because if you do that, it's usually going to cancel out nicely like what happened here. Okay, so Quiz Wednesday. Dr. Gerstel, for the Quiz Wednesday, are we going to have to do something involving horribly nasty square roots? No. I mean, it's always an option. I can always change my mind. I'm the professor. I can do what I want. But, no. So for the Quiz Wednesday, I'll tell you exactly what to expect. You can expect to have to take a derivative using this limiting process. But it'll be one like the first ones where you can kind of pull out factors of h from the top and bottom right away and can't cancel out. And it's not going to be one like this one where there's a lot of more advanced trickery going on. Maybe on the exam I'll give you one later. All right, have a good rest of your day, everybody, and I will see you all on Wednesday. Yes. Sure, not a problem. See you tomorrow. Well, then you are in a sad place. In that case, send me an email, and we can probably make something work out. Like, are there any times close to my office hours that you can come by? Take care.
Yes. Yeah, I can come before 1.
Tomorrow?
Yes. I'm trying to think, yes.
Okay, yeah, if you wanna come at like 12:45 or something, I can make that work. Send me an email to remind me we had this conversation.
Thank you.
Sure.
Okay.
Yeah, do you just wanna do all of them at once?
Probably, yeah.
Okay, send me an email to remind me and, I will be ready for you then.
Sounds good, thank you.
Sorry, should I email you to schedule my makeup quizzes as well?
Yes.
Okay.
Yeah, just send me an email, let me know when you wanna come by. If you wanna take like multiple quizzes at once to make them up,
Okay.
since you were out for a while,
Yeah.
that's perfectly fine. Or you
Do we
can
go-
do like one at a time.
Do we do 2 of them? Because I don't think I took standard 2.
Uh,
I know I didn't take standard.
I don't remember offhand, but, say, you did standard 1, I'm pretty sure.
Yeah, I did standard 1. I know I didn't do 2, and then I don't know, we did 3 already.
Yeah, we did 3 already,
Okay.
so you probably missed 2 and 3. So yeah, you
Okay.
can come by and take both of those later.
Okay, thank you.
No problem.
I was just gonna ask if it's possible if I retest standard 2 at 2 today?
Sure thing. Send me
an email?
Yes.
Gotcha.
Send me an email send me an email to remind me, and that should be perfectly fine.
Got it. Thank you.
See you in a bit.